Don't forget, I'll remind you guys that this is going on the internet. So if you have problems with your name getting out there, you should definitely change your name to just your first name with your first letter of your last name on it. So you might want to do that, at least change your username. I have looked at the videos that are going up, and they constantly have that little window over in the right where I'm talking. And when you guys talk, it's got your names listed up there. And if you occasionally your face pops up. So I just want to make sure everybody knows that. If you have something like that and you can't allow your, face or name to be on the internet, you need to definitely email me and let me know. But in the meantime, like I said, just for your own personal safety, you might want to just change your username in Zoom to your first name and then maybe space and the first letter of your last name. And just to repeat, it looks like a couple of you done it, but yeah, you can go ahead and chat me your first and last name. Send your first and last name in chat, and that'll be our role for this class. So, anybody have any questions? All right, looks like just about everybody has chatted me your first and last name, so that's good. I guess we should go ahead and get started. I'll open up again one more time since now it is officially 5:20. I want to reiterate this video is going online. I've told you before, but I wanted to make sure everybody knows it's going online. So if you have a problem with your name or your face popping up on the internet and others possibly seeing it, then you need to let me know that that's a problem. You don't have to give me any details about why or anything like that. You just have to tell me. And then the other thing is, either way, you probably should change your username to just your first name and the first letter of your last name as opposed to the whole name. Okay. You don't have to do that, but like I said, it's not anybody's business who's taking what classes at what time and all that good stuff. So that's all. So again, no questions. All right. Well, we're going to start on then. So last time we talked, I showed you a technique where we argued, and I don't think I did that good of a job of it. I might take another poke at it with Excel and motivating the actual equations of kinematics, specifically the first 4 to 6 equations of kinematics. Uh, I wanted to motivate you into coming up with the definitions ourselves, specifically the definition of average speed. Then I had to tweak it a little bit so you'd understand the difference between average speed and average velocity. But you sort of saw how they're similar. But I also explained in the case of a small child, uh, let's say playing t-ball, if the small child, hits the ball, takes off running, uh, touches the home plate somewhere or very near to home plate as they're running to first. Then they round first, go to second, round second, go to third, round third, go to home, and then they tag somewhere on the home plate. Then that average speed for that scenario would be the sum of the four distances. So basically, let's say it's 60 feet. It'll be 60 feet from home plate to first, 60 feet from first to second, 60 feet from second to third, 60 feet from third to home. That's 240 feet. And let's say it took 12 seconds. That would be 20 feet per second is their speed. Okay. That's obviously a very high velocity for a kid running, but in this case, it's the average speed. Now, when you go to calculate the average velocity, it would be the final position minus the initial position. And if the child actually stepped on home plate when he left and then stepped on that exact spot when he returned, then the final position minus initial position would actually be zero and the average velocity would be zero, even though the average speed is, 20 feet per second. Or if he didn't actually specifically hit exactly the same spot, it's going to be within, a half a foot or so, maybe a foot at most of hitting that exact same spot again. So X final minus X initial in that case, worst case scenario might be 1 foot. So it'd be 1 foot divided by 20 seconds, which would be 0.05 feet per second. So it's important that you understand the difference, at least in terms of the average speed versus the average velocity. So I had to motivate that a little bit with the average velocity formula. And then I use the idea of 0 to 60 in 4.0 seconds to come up with a definition that I think y'all were on board with of what acceleration is. And acceleration, of course, is the change in velocity divided by the change in time. At least that's the average one. But if you allow the time interval between the first velocity and the last velocity, if you allow that time interval to get really, really small, you can make the time interval so small that the velocity can't change horribly from the one time, from the beginning of the time to the end of the time, in which case you're slowly finding out what the instantaneous acceleration is as opposed to the average acceleration. And that's the same process that we went through with average velocity to instantaneous velocity. We allowed the delta t to go to essentially zero by a limiting process. And then the average velocity, which was delta x over delta t, becomes the limit as delta t approaches zero of delta x over delta t, which we know of as dx dt. Okay, so that's what I was trying to do, was motivate or inspire you to come up with that idea of average speed, specifically from the units that your speedometer reads, which, you know, it reads miles per hour. And I want you all, probably for the rest of your life, to think of the word per as meaning division, at least when you're talking about mathematical or physical things. So when I say miles per hour, that means miles divided by hours. And since mile is a unit of distance and hour is a unit of time, you would say the average speed is distance divided by time. Okay. That's what we came up with. So now that we've done that, I want to work some more examples. From that, remember, I was able to integrate the acceleration, which I assumed was a constant. So if we pretend a is equal to a constant, a being the acceleration, then we can use the fact that a is equal to dv dt, integrate that, and that'll give us the velocity as a function of time. But we needed an initial condition because, as you know, when you integrate something without a range of integration, then you have to introduce a integration constant. And what we discovered was that if you plug in t equals zero in that resulting differential equation, then what you get is c is equal to whatever the velocity was at t equals zero. So that actually allowed us to evaluate that integration constant. And therefore, you know that you need evidently one initial condition if you're trying to integrate a equals dv dt to get v of t. You have to have one initial condition. Specifically, the velocity at t equals zero would work, but you could, in principle, find out it from other values. Like if you had the velocity at 2 seconds, you could plug that in. It'd be harder math, but you could still get it. Okay. Then, given that you have v of t, you have v of t is equal to, you know, something. In fact, it turned out to be v initial plus at, where again, a is a constant. Now, v initial plus at is equal to the derivative of x with respect to time. So you could integrate that again. And again, using the no limits of integration required us to have an integration constant. And we basically came up with another equation. And then we used the idea that if I plugged in t equals zero, then all that would be left in that solution to that differential equation is c would be left on one side, and the other side would be left x of t equal to zero. So we know that that integration constant turns out to be the initial position x sub zero or x sub I. Okay. So that process was very important, and I warned you that it was actually a process that we use when the acceleration is not a constant. Because if the acceleration is not a constant, those equations we got from it just don't work. So let me start by sharing my iPad screen, and on this iPad screen, I have a recap of the equations, and I've got them numbered because we're going to be making use of it. So you might, you know, feel compelled to take a picture of the screen or something. Of course, you can also just download the notes later. That would be fine. But here's my iPad screen. Should come up any second now. Okay. So what I've done is I've taken the time to write out the individual equations that we found, and I also decided to include the special conditions where they existed. So the first thing we motivated was equation one, which you see is the average speed equation. And I showed you the two symbols that we can possibly use for average. I can use S with a bar over it for S for the speed and the bar over it meaning the average. Or I can put the S in a less than and a greater than symbol between them, as you see in that second spot. That's also another way of saying the average speed. And then, of course, I wrote it in word form so you just know what I was talking about. And what we ultimately decided on was the average speed was equal to the distance traveled divided by the time taken. And it's very important that you understand it's the distance traveled. That even means if you go a ways and then turn around and come back and do a bunch of this, and then you come to a stop at the final position, you have to add up all those little distances because that's really what matters. All of that distance matters in the average speed. Now, the next one was the average velocity, which in this case, I didn't necessarily talk to you about last time, but we had to take the final position, which is listed because we're just talking about one-dimensional motion. Everything's along the x-axis. So the final position is x sub f, and the initial position is x sub I, and we have to take the difference between those two. That difference that difference is called the displacement. Okay, and that's another vector quantity. Again, we'll learn about vectors in chapter 3, but that is another vector quantity, and it has a very specific meaning. It's basically that is supposed to be a vector, which you can represent as an arrow that points from xi to xf. So that's what that displacement is. It's a vector that, or an arrow, the non-pointy side of the arrow is sitting on x sub I, and the pointy side of the arrow is pointing on x sub f. And of course, that has a length that is a numerical value like 3 meters or 3.78 meters or something like that. And then you have a time interval, t final minus t initial, which, by the way, almost all the time the t initial is 0, but I show it in here a couple times. But anyways, often you can just throw out the t initial because you started your stopwatch when you started looking at the motion. But when you do that displacement, the numerical value of the length divided by the numerical value of the time elapsed, you get the numerical value of the average velocity. And since that displacement vector is that small vector that goes from xi to xf, in the case of the child running around the t-ball field, the xf and xi were either the same spot or very close to each other, and you immediately see why the displacement is quite small. Now, since the displacement is a vector, it also has a direction, and that's really what makes it ultimately a vector, is having a direction and magnitude, as we learned from Despicable Me 1. Okay, now I also use that same sort of premise and the fact that 0 to 60 was really the most direct measurement of acceleration that a car dealership can give me. For instance, when they said, let's say a Mustang, a new Mustang, we used to call the Mustang GTs. They had the 5.0 liter engine, which is the 302 cubic inches. That 5 liter engine, we can pretend allows a 0 to 60 in 4.0 seconds, 4.00 seconds. That's actually a pretty good 0 to 60 time. It literally means it takes only 4 seconds for you to get from 0 to 60 miles per hour if you're forced to pull out in front of someone moving 60 miles per hour. As long as you've got 4 seconds of time, you should be good to go, right? So if you look at that, that 0 to 60 means there's an initial velocity and a final velocity. And the fact that they said 0 to 60 means the initial velocity is 0 and the final velocity is 60 miles per hour. And then they gave us a time elapsed, which was 4 seconds. So that's the delta t. So you can sort of guess from that, oh, they must want to divide the change in velocity by the change in time, which is just like what we did with average velocity. Only in that case, we did the change in position divided by the change in time. And then with average speed, we did the distance traveled divided by the time taken. So we were able to come up with a fairly good example or a fairly good explanation of how to go about calculating the average acceleration, which you see as delta V over delta T. Okay. Now I labeled that one 3, and then I said V equals VI plus AT, and I also labeled that one 3. That's because the equation 3 that's on the left, the VF minus VI over TF minus TI is equal to A bar. If you actually solve that for V final, then you'll get that other equation 3. We got that other equation 3 when I did the first integral by setting A, the acceleration, equal to a constant, and then setting that constant A equal to dv dt and integrating it. So we came up with another equation that really is the same as the equation for the average acceleration, but it's a kinematic equation at that point. So I just wanted to make sure y'all understood that these were identical equations. And to and to further make the point that they were identical equations, down here at the very bottom it says also x is equal to xf. That means if I just take an x and label it, you can understand that that means the final one. Similarly, x0 is the same thing as xi because I will often write x final minus x0, or I'll often write x final minus xi. So that's why I'm writing that. Then v final can also be v with no subscript. It can be v final with the f subscript, or it can be v2 with a 2 subscript. And similarly, v initial could be v0, but it can also be vi with an I subscript, but it also can be V1, which you'll see when you look at equation 8. That's why I'm bringing out the ones and the twos. All right. Now, after getting the V equals VI plus AT that I got last time, I then set that V equal to dx dt. In other words, I set the VI plus AT equal to equation 4, and then I integrated it. Okay. When I integrated that, it actually gave me equation 6. Now, that equation 6 was derived specifically in the case of A equals a constant. That's why I wrote A equals constant next to it, because you can't use that equation unless one, the acceleration is constant, or two, you're making the assumption that the acceleration is constant because it's not changing horribly much, or maybe because that's the only way you could get an answer and you're trying to get at least a guess at what the answer would be. That's not necessarily good science, but it's a way where you can get your foot in the door. And if you later find more out about the acceleration, you can adjust it and treat it as a constant acceleration for a smaller time interval, work out the math for that smaller time interval, then get another value for acceleration for the next small time interval, work that out, and keep doing it iteratively like that. You can do it. Okay. So either way, the big point is we did get ultimately x equals 1/2 at squared plus v0t plus x0. And since that was predicated on us being able to say a is equal to a constant, that equation is only valid when a is a constant. Now, once I had that, I said, what if we wanted to know, let's say, the final velocity, but we didn't necessarily want time and we didn't know time? Well, we can take equation 3, solve that for A, and plug that into equation 6, and that's how we got equation 7. I did that in the last class. You can check on the video of it, or you can look in the notes. So again, that equation also requires A equal to a constant. Now, one I didn't give you, but one I found useful on occasion is equation 8. It turns out that if you assume the acceleration is a constant, then you can always calculate the average velocity just by taking some initial velocity plus some final velocity, adding them, and dividing by 2. Okay, but that's literally only valid when the A is equal to a constant. And I also put down here equation 2, because if we take equation 2 up at the top where it had V average, if I solve that for x final like I did with equation 3, then I get equation 2, which is x is equal to x initial plus v bar times t. That's true no matter if the acceleration is constant or not, so I didn't put that in there. Okay. So those are what we call our kinematic equations. Let me write that word down. Okay. So, what we're studying in this first half of the course is basically Newtonian physics. And Newtonian physics is sort of broken down into two parts, kinematics and dynamics. So, kinematics is the study of motion without consideration about how you make the motion happen, but rather what are the consequences of the motion. So, for instance, if I took a ball out there and I gave it a equation, say, that represents the position as a function of time, or another equation that represents the velocity as a function of time, or a different equation that represents the acceleration as a function of time. We don't necessarily care in kinematics what caused those equations to be valid, but we do care what that means. So, for instance, what happens if I let the ball travel for twice as long as I do in the first case? How does that affect the distance? What about the velocity? How does it affect the velocity? What about the acceleration? How does it affect the acceleration? That's what we mean by kinematics. The dynamics comes in when we start to consider what do I have to do to make something have an acceleration that is a constant? What about something that has an acceleration that's not a constant? What about what makes the velocity change? How do you Sorry, I don't know what happened. It seems like Zoom crashed. I don't know exactly where I lost you, so I'll sort of overlap a little bit, but I also have to share my screen with you again. So let me do that. Okay. So what I was telling you is kinematics is the study of motion for motion's sake, but without actually trying to figure out what causes that motion to be what it is. Dynamics is where we use specifically, we'll use forces, but there's other ways we can do it too. But we'll use forces, and forces can help us understand how to make the particular motions. How do we make something accelerate, or how do we make something hold on to the same velocity but change, or the same speed but change the velocity by just changing the direction, that kind of stuff. Okay. So now that I've sort of given you this recap of the equations, I'm going to make use of these numbers as we're doing this next problem. So, does anybody have a question on this before I move to the first example? Okay. Now notice last yesterday the same thing happened where the Zoom canceled out and then came back, but all the videos stayed there. So I had the video before it collapsed, the video after it collapsed, and it just sort of seamlessly ran into it. I'm hoping the same thing will happen this time. If not, we're just not going to get that beginning part. So I'm just going to go from here and say these are the equations we derived last time, and now I'm going to use them. So let me turn to our first example. Example one, the acceleration of a particular car has been found to be given by A of t is equal to 6t minus 8. Okay. Part one, what unit must the 6 have? Does anybody think they have any idea of that? This is a continuance of chapter one material where we did unit analysis and dimensional analysis. I tried to show you the hardest stuff, which is generating actual forms of equations. That's the hardest stuff with unit analysis or dimension analysis. But some of the unit analysis is literally just like this. Someone gives you an equation. A of t is equal to 6t minus 8. All you have to focus on right now is the 6t term. Can you look at that 6t, knowing what the units t must have and knowing the units that a must have? Can you tell me what unit the 6 must have? Okay. Let me pull up the chat window just in case someone's answering it there. This is really a pain in my butt. I go up here and it doesn't always show what I need it to show. There it is. Okay, so now I've got the ability to put chat window down here. Newtonian motion in terms of the resulting motion, not the cause of the motion. Ah, you said meters per second cubed, and you're exactly right. Okay. The reason why Daniel was able to conclude that was, I'm going to write it right here. Number one, A of t in unit wise has to have dimensions of meters per second every second, and t has to have units of seconds. So A of t equals 6 times the units of t, means the units of 6 would equal the unit of A of t divided by the unit of t. That's a way you can actually work it out algebraically. And we get that the unit of 6 is equal to meters per second every second divided by seconds, which is equal to meters per second every second times 1 over seconds, which equals meters per second cubed. And that's exactly right, Daniel. Okay. Yeah, it's Daniel. Now, for the other part of 1, what about the 8? Can anybody tell me what units the negative 8 would have? Chloe says meters per second, and she's exactly right. Notice how I'm saying that? It is a completely correct to write meters per second squared. It's completely correct to say meters per second squared, but hopefully in your attempt to understand acceleration, you'll adopt this practice, which is calling it meters per second, so that you can think of it as, oh, if an object has an acceleration of 2 meters per second, that means if I start at t equals 0 with 0 velocity, then after 1 second, the velocity is going to change by 2 meters per second each second. So it'll go from 0 meters per second to 2 meters per second. And then after the next second, it'll add another 2 meters per second. So it'll be 4 meters per second. And then after another, it'll be 6. So that's the reason for me saying meters per second per second. Again, I've learned that helps students over time. In this case, the negative 8, which is being added to the other term, the 6t term, therefore it has to have the same units as the 6t term, or the fact that it's a term all by itself means it has to have the same units as the A of t. So you can say it is meters per second every second. And that's the answer to that. Okay. Now here's where it gets interesting. Number 2. If the car had a velocity of 5.00 meters per second at t equals 0.00 seconds, then what is v of t? And then part 3, if the car had a position of x equals negative 2.00 meters at t equals 0.00 seconds, then what is x of t? Okay, so what this is me showing you exactly the type of question I would ask you if I wanted you to do what we did last time, which is do that integration twice to find x of t from a of t. When we did it last time, we came up with x of t being equation 6, and we came up with v of t being equation 3. So this time, we're going to start with we have an a of t, so we're going to start with 5. So I'm going to say equation 5 gives me 6t minus 8, and I leave a significant space. According to equation 5, a is supposed to be equal to dv dt. So I'm going to write with a space in front of it, dv dt. That's what we call a first order differential equation because there's a derivative in it, and the derivative is the first derivative. If the derivative was a second order derivative, we'd call it a second order differential equation. If the derivative was a third derivative, we call it a third order, and so on and so forth. Okay. These are actually really simple differential equations, though, but they also teach us something about the more general aspects of differential equation. So we have an equation, and we know from basic algebra that whatever we do to one side, we must do to the other. And I've told you that the integration is just repeated addition. And of course, it's perfectly okay to add something to one side of the equation as long as you do it to the other side. It's also okay to multiply one side of the equation by a number as long as you multiply the other side by the number. Now, there are some rules. For instance, you can't multiply it by zero. Even if you did it by accident, not knowing, you could actually make the two sides of the equation not equal anymore, and you'd get something weird like 3 equals 2. So that's one thing you can't do. Another thing you can't do is multiply by 1 over 0 because 1 over 0 is undefined. So it's also equivalent to say you can't divide both sides of the equation by 0. Okay. So I am going to multiply both sides by dt first. And just to show you that that's another step, I'll write it with a different color. And now I'm going to integrate both sides. But unlike last time where I didn't put any limits on the integration, I didn't integrate from point A to point B. I just did a indirect integral. What's the word I'm looking for? Indeterminate integral. I think that's it. Maybe that's not. Anyways, I did the integral where we had the integration constant. This time, since I have information about stuff, I'm going to actually integrate it from a range of integration. So the left-hand side is integrating with respect to t. I'm going to integrate from t equals 0 to just plain t. The right-hand side, you'll look and see that the dt's are sort of canceling out. So I know what I'm actually integrating is dv. And the fundamental theorem of calculus says the integral of dv is v. But since I evaluated the left-hand side at t equals 0, then the left-hand side or the right-hand side has to be evaluated at t equals 0. So that's going to be v of 0. And since I'm doing the left-hand side at t, the right-hand side has to be evaluated at t. So that's v at t. So that's my limits of integration. Now all I have to do is do the integral. I'm going to switch back to blue. So the integral of 6t is 1/2 of 6t squared because, of course, when you integrate, you have to increase the exponent by +1 and then divide by that new exponent, which is, n plus 1, which is in this case is 2. So it's 1/2 times 6 times t squared. 1/2 of 6 is 3. So I'm just going to call that 3t squared minus 8t because the integral of -8 is just -8t. Now I'm evaluating that at t at the top and at t equals 0 at the bottom. So when I plug in t for the top, I get 3t squared minus 8t. And then I'm supposed to write minus and then a left parenthesis. And then I evaluate 3t squared where t is 0 minus 8t where t is 0 and then close parentheses. You can see that just equals 0. So basically the answer for this subtraction is just 3t squared minus 8t. On the other side, I just get v of t minus v of 0. Okay. Remember, v of 0 means the velocity that the object had when t was equal to 0 seconds. So if I look up in the problem, what that tells me is this v0 is 5.00 meters per second. So what I have is a 3t squared minus 8t on the left and a v of t minus 5 meters per second on the right. I'm going to add the 5 meters per second to both sides. And finally, when I do that, I will get v of t, which we might also just call v, is equal to 3t squared minus 8t. and then adding 5 meters per second to both sides is going to give me plus 5. And notice it should be two decimal places, but I'm just writing it as 5. I'm not writing the units because I showed you in part 1 exactly how to determine what the units are, and you have to assume that's what they are anyways. So what I now have is a very specific equation for the velocity as a function of time, which is exactly what they asked me for in part 2. Okay. Now, this also means that I can use equation 4. So using equation 4, what I can say is 3t squared minus 8t plus 5 is equal to dx dt. Okay, so that's what equation 4 says. Notice equation 4 just says the velocity, which is instantaneous, so that's velocity at a certain particular time, v of t, is equal to dx dt. So that's all I did there. No big deal. Now I'm going to do like I did before. I'm going to multiply by dt on both sides. And then I'm going to integrate both sides like that. So again, I'm going to integrate from t equals 0 to t. So this side's going to become x of 0 to x of t. I will tell you that in general, the mathematicians do not like us integrating to t when our variable of integration is t. So, they would prefer me write 3t prime squared minus 8t prime plus 5 dt prime, and then integrate that and then plug in the t for it. That would be fine. Okay. But we're just ignoring that. I'm just telling you this is the way we do it in physics. And it's not clean as it would like to be, as you would like it to be as a mathematician, but it's okay. Okay. So the same thing's going to happen here that happened before. I am going to have to evaluate the integral at the ranges. So what I get here is integrating 3t squared. That's going to become 1/3 of 3t cubed. So I'm going to get 1t cubed. And then the integral of negative 8t is negative 1/2 8t squared. And of course, 1/2 of 8 is 4. So I'm going to say minus 4t squared. And then the integral of 5 is 5t. And then I have to evaluate that at t equals 0, which I think you can see if I plugged in t equals 0, I get 0. And I also have to evaluate it at t, and you'd see that when I evaluate it at t, I get that exact same response, 1t cubed minus 4t squared plus 5t. So that's really all the left-hand side turns out to be. The right-hand side, on the other hand, is going to become x of t minus x evaluated at 0, which if we look up at the problem, we see that x was equal to negative 2.00 meters at t equals 0.00 seconds. So this little x of 0 is actually negative 2.00 meters. Okay. So I'm going to notice that's a minus of a negative 2, so that's a positive. So I have to subtract 2 from both sides. When I do that, I get that x, which is also x of t, is equal to 1 t cubed. I'm just being pedantic putting that one there. I don't have to stress it out so much, but I want you guys to think that that is an actual constant out there that has units. So if you didn't think of that number one there, you sort of might get by with thinking that there's no units out there either. So I'm just putting that in there so you will remember that it does have units. So that's 1t cubed. Whoa, Nelly. I switched to writing the wrong thing. Minus 4t squared plus 5t. And then remember, I subtracted 2 from both sides, so that's minus 2. That is technically 2.00 meters, but again, we're just writing it like we would in math. And what I now have is the position as a function of time. You could call this the trajectory, for instance, but it's basically it, and that's the function that we were actually asked to find. So this is basically the same process I went through last time, but for the case where the acceleration is not constant. Anybody have any questions on this? Okay. Now you'll notice these examples that I'm working are not the examples in the book. I think the examples in the book are super, super straightforward and super, super easy. I'm trying to work the more difficult ones, which is stuff like this. And also I'm hinging on the fact that I've had years and years using these same test banks that I've been using in similar test banks with other textbooks. And I repeatedly know that or I repeatedly find that there's a specific problem that gives students a problem, and I'm trying to address that. This is one of those problems. So this is something you need to be able to do. Okay. Now, that being said, this is probably the hardest aspect of chapter 2, period. So in that sense, if you can get this done, there's no reason you can't do any other problem in chapter 2. Okay. But now I'm going to do another example using the same example. And this time I'm going to tackle a different problem that students have had. So let's call this example 2. Consider the previous example and the answers we got. Ooh, I shouldn't have capitalized that. What is the average velocity between t equals 0.00 seconds and t equals 3.00 seconds? Okay. So this time we're actually asked for the average velocity between t equals 0 and t equals 3 seconds. Okay. I will point back to the average velocity formula, which is equation 2. And what I'm going to do is say solution. Equation 2 says average velocity is equal to x final minus x initial over t final minus t initial, which strictly speaking would be x of 3.00 seconds minus x of 0.00 seconds minus 3.00 seconds minus 0.00 seconds. Notice that t initial being 0.0, that's what I mean by we often just drop the t initial because it's obviously not there. Now, that being said, we have an expression for the position as a function of time. And that expression is t cubed minus 4t squared plus 5t. So x of t equals t cubed minus 4t squared, I think. Let's double check. Yes. Minus 4t squared plus 5t minus 2. I think that's all right. Let's double check again. Yes, that is correct. So we've got all that written out. So what I want to do is find x of 0, which should be really, really easy. That's 0 cubed minus 4 times 0 squared plus 5 times 0 minus 2. And notice everything's 0 except for that minus 2. So the answer is negative 2.00 meters. That's where I just happened to recall that the x of 0 is not only 2, it's 2.00 meters. So I had the units and everything. Now I've got to do the same thing for x of 3.00 seconds. In this case, it's 3.00 seconds cubed. Remember, there was a 1 out in front, and that 1 ultimately has to have the appropriate units, which would obviously be meters per second to the fifth power. Okay, so just so it would work out, or actually it would be, no, just meters per second to the third power. I was thinking that was the acceleration equation. So we've got that. Then we say minus 4 times 3.00 seconds squared, and then plus 5 times 3.00 seconds, and then minus 2. So 3 squared is going to give me 9. 3 squared is 9 times 4. That would be minus 36. And then 5 times 3 is 15. So I'm going to say plus 15 and then minus 2. And I know all those units should work out to be meters. But what I'm going to do is say 9 plus 15 is 24. Minus 2 is 22. Minus 36 is, and just to keep from making a careless arithmetic mistake, I'm going to do all this in the calculator just to be sure. So 9 minus 36 plus 15 minus 2, that gives me negative 14. Now, all of these numbers had, well, the 3 squared should have made 9.00, so it had 2 decimal places. The same thing with the 4 times 3 squared. That should have had 2 decimal places. We're adding, so that's why I'm thinking about decimal places instead of sig figs. 3 times 5 was 15, and that should actually only have 1 decimal place. And then the 2 actually had 2 decimal places. So that last little 0 there is not technically a significant figure. So now we can go ahead and calculate what our average velocity is. Our average
So,
velocity.
Professor,
Yes.
like Charles was saying, that should be 27, not 9.
Okay, thank you. Yep, 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 yep. That's yeah, I can't believe I made that mistake, but I appreciate it. Thanks, Charles, and I think it was Daniel. Yeah, Bonehead, 3 times 3 is 27. Thank you. That actually, I was wondering why it came up to be a negative because I made this problem up earlier and I didn't recall getting a negative, and it worried me a little bit. So, but I also had changed things around since then, so there was some chance of. So yes, 3 times 3 is 9 times 3 again is 27. Thank you for that. And I'm always one to make a really bad arithmetic mistake. So now I can do this. I was wise to use my calculator. I was just late to do it. So I'm gonna say 27. Now that's still 9. 3 squared is still 9 there. 9 times 4 is still 36. So I'm going to say 27 minus 36 plus 15 and then minus 2. And that gives me 4. That's much better. And this Yeah, this should be probably one sig fig or one decimal place here. I'll call it like that. Not a big deal. Now, this tells us that our average velocity is x of 3 seconds, which is 4.00 meters. Yeah, it's definitely one decimal. Okay, yeah, I was just double checking that. Minus x of 0, which is negative 2.00 meters. That one actually did have uh, two decimal places. And then I'm dividing it by 3 minus 0, which is 3.00. Notice we get 4 minus negative 2, that's 4 plus 2, which is 6. 6 divided by 3 is 2. So this is 2.00 meters per second, but the second zero is not a sig fig. Okay. Any questions on that other than my gooby arithmetic mistake? Indefinite interval. Thank you. I couldn't think of that word. I hate it when a word just this doesn't come to you. All right, so now I'm going to try example 3, and this is the part students usually get this one, but I think it's sort of luck. But the example 3 is what makes me think that one's luck because they don't get it right at all. So I'm going to do something now that is traditionally hard for my students. So let's make sure we can all do it pretty well. Uh, Here we go. Let's write out example 3. And this one is, okay, so this problem is like the last one, except we're calculating the average speed instead of the average velocity. So I'm going to say solution, and I'm going to say equation 1 tells us that speed is distance traveled divided by time taken. Okay. And we also have that x of t is equal to t cubed minus 4t squared plus 5t minus 2. Okay. So what I need to figure out here is how far this thing has actually traveled. Now, we are doing just one-dimensional motion, so everything is going to be right along the x-axis. It can go like this and this, but the problem is along the x-axis, if you consider what the graph is, like x of t, you would see that the x is always sticking along the x-axis, but the t allows it to do different things. And we got to figure out exactly how far they move. So if I just did like I did for the velocity, and I took the x at 3 seconds minus the x at 0 seconds, I would just get a distance of 4 meters. But what if there was a bunch of curves in between 0 seconds and 4 seconds? And in fact, I made this problem up this way on purpose. So let's take a break for a second from this. And now I'm going to start sharing another screen, which is Desmos. Okay. So now let me share this screen. Okay. So what I'm going to do is take and plug in that equation I had. Now I'm doing x equal to a function of t, but in Desmos I got to write y as a function of x, I think. So I'm going to do it like that. So it's going to be equal to uh, x cubed minus 4x squared plus 5x, and then minus 2 is just going to shift it straight down like that. Okay. Now I need to figure out how much this thing moves between t equals 0 seconds and t equals 3 seconds. So I'm going to type in x equals 0 and x equals 3. And what I can see is x is equal to 3 when, or excuse me, time is equal to 3 when x is 4 meters. So I'm going to write that down on my iPad. I'm not showing you the iPad yet, but I'm going to write it down. So uh, at t equal 3.00 second, x is equal to 4.00 meters. Now I'm also going to look at 0 seconds, which looks like right here. And sure enough, at t equals 0.00 second, we already knew this, but still, x is equal to negative 2.00 meters. So I've got that information down. And what I see is the graph comes up from -2. It goes up and hits the x-axis, or what we call the time axis, at 1 second. And that is a height of 0, obviously. And then it goes all the way down to hit this spot, which is 1 2/3 seconds. It's going to hit a height of negative 0.14815. So what I'm going to do, I'm drawing this on my iPad right now, and I'm showing it to you for a second. So I just want to get an idea of exactly what happened. So what I had was over here, this would be -1, and right here be -2. It went up. I'm going to say this is 1, and this is 2, and this is 3. Now, what it seems to have done is it went up from here to 1, and then it dropped down between the 1 and the 2, and then came back through the 2 and went all the way up to this value, which we found was 4.00. Okay. And now this value, again, I'm saying this like you're looking at it. I know you're not looking at it. I just wanted to let you know I do remember that. But now this little point, I'm talking about this little point right here. That is basically what we're talking about 2/3. So this would be 2, this would be 4/3, would be 1 1/3. So it's 5/3 and negative 0.14815. So that's what that data point is there. Okay. The other one, of course, was 0. So now you look at this, what I want you to understand is the distance it traveled from here to here is in fact no different than -2 meters up to 0 meters. So the person has, or the vehicle has gone 2 meters up to this first black dot. Then it's gone an additional 0.14815 meters downward. Then it's gone another 0.14815 upward. And then it goes an additional 4 upwards. So the total distance has to be the sum of all those. So writing that down, I'm going to say distance traveled is actually equal to 0 minus -2 plus, notice I'm adding the distances and nothing's considered a negative distance when you're talking about speed. So I'm making up ways to sort of work that out. So now I'm going to take negative 0.14815 meters minus 0 meters. And actually, I should do it the other way. I should do 0 meters minus negative 0.14815 meters. And then I'm going to do plus 0.14815 meters again. This is coming back to hit the horizontal axis at t equal 2 seconds. And then I've got to go all the way back up to 4 meters. So I'll say plus 4.00. Now, I've explained all that. I basically found out what distance this is and going from -2 on the X number line to 0. Obviously, that's 2 meters. And then going from 0 on the X number line to 0.14815 negative. So that distance is 0.14815. And then the distance from going there up to the horizontal axis is again 0.14815. And then the distance we traveled in going from 0 up to here was 4. Okay. So I've explained all that and how I got all that. Now I'm going to go ahead and show you it on my iPad. So I'm going to do share again just because it's so fast and untime consuming. Okay, so notice what I did is I did a little representation of the diagram of the actual graph. I showed where it peaked and that sort of stuff. I even wrote down the critical data. And then I said, okay, this is what I'm actually doing in computing these distances. Let's say, from this spot right here to this spot, notice that's a distance of 2 meters. That's all we care about is the vertical distance. And then from this spot to this spot, that distance is 0.14815. You're going in the negative direction, but we need the total distance traveled so we don't count the negatives as if they're subtracting miles. We add them up. So I get another 0.14815. That's what that is. And then from this point to this point, I go from 0.14815 up to 0. So that's the other 0.14815. And then from 0, I go from 0 all the way up to here. And that distance, of course, is 4. And that's where that came in. So hopefully everybody understands why I did that. Did anybody have any questions on that before I write the actual answer out? So I'm going to do 2.00 meters. So 2 plus 0.148, oops, 815 plus 0.14815 plus 4, and that gives me 6.2963. Now, really, these were only good to uh, two decimal places. So this number and this number is not a sig fig. So now I can say the average speed is 6.2963 meters divided by this time. The time is still 3 seconds minus 0 seconds. So that's, oops, might help if I write with a pen. That's equal to 3.00 seconds. So I'm going to divide that by 3, and this gives me a average speed of 2.099 meters per second. But that's really 3 sig figs divided by 3 sig figs. So we would call this 2.10 meters per second. Any questions on that? Okay. So that 2.099, this is a tough problem, but you are allowed to use a graphing calculator in my class. You're not allowed to use Desmos, but you are allowed to use a graphing calculator. That being said, you don't have to actually graph this, but you do have to still figure out some stuff about the graphs. So if you turn the dial back to the first semester of pre-calc, there was a lot of stuff you did to learn how to graph polynomial functions. All of that is fair play, but now in addition to those tools you learned in pre-calc, you have the tools of calculus. What really made this a problem was the fact that this actual x of t had a maxima in between 0 seconds and 3 seconds. It had a maxima, and then it had a point of inflection, then it had a minima. Okay. Because of that, there was overlaps in distances and all that good stuff. So what you need to know is really what are those minima and maxima and what points do they correspond to so that you can just figure out, in this particular graph, what you would do is you'd figure out from t equals 0 to t equal 1 that the function is an increasing function. Okay, so you just draw a line with a positive slope going up and to the right. And what you'd find at t equals 1 second, by taking the derivative setting it equal to 0, you would get 1.00 as a maxima. You wouldn't know that until you took the second derivative, but these are really easy derivatives to take. When you took the second derivative, you find that you got a negative, so you'd figure out that that's a maxima. So you'd put a little, uh, concave down shape there. Then you would take this derivative, set it equals 0. You'd find the other function happens to be basically occurring at 5/3, t equals 5/3. So when you did that, you would say, well, what's the function between t equals 1 second and t equals 2 seconds? And what you'd find is that part of it is a decreasing function and another part of it is an increasing function. And you know that the point where it switches from decreasing to increasing is at a minima. So that x equals 5/3 is your minima. So you'd show a down and to the left curve from the maxima down to the minima. Then you'd show a little concave up shape at the minima. And then you could also find that from that time interval, which is around, like I said, 5/3, from there all the way up to 4, it's just an increasing function. So it go like that. So really all you need to know is the peak height here, the trough depth here, and then this final number and this final number, because it just does this. So the change is just 2 meters. It just does this. So the change is just 0.14815. And then it does it again. So it's another 0.14815. And then it goes from 0 to 4. So you add another 4 to it. So you don't technically have to do any graphing at all. It's just you have to understand how graphs work. remember a third order polynomial has like a, well, let's start with a quadratic because that's one you probably know. A quadratic like ax squared plus bx plus c equals 0, that has up to two zeros. And it also has up to two minima, basically, or maxima, extrema, whatever you want to call it. So you can figure out from that that, obviously a polynomial of order two is going to have a parabolic type shape, or there's some weird ways you could do it where you get basically just a straight line or a diagonal line or something. You could do a third order polynomial, and then that has to have up to three zeros. And with three zeros, that means it crosses the axis at three different spots. So it could be coming down and then down, switch to up back through here, and then up, switch to down back through here and hit that. So it's either going to be, left arm up, right arm down, or it's going to be left arm down, right arm up, and it's going to have some wiggling in the middle of that. That's just the way functions behave. So you do need to understand that. And not only that, I'll just remind you that one of the terrible things about physics is that when you're taking it, your textbook author and therefore all the homeworks that your instructor is assigning, and maybe your instructor themselves, is it going on the assumption that you've learned everything you could have learned from the appropriate classes that are prerequisites for this. So we're assuming that you remember everything that you ever learned in, I'll say, uh, high school, elementary school, middle school, all your history, all your math, all your science, all that stuff. We're just assuming you know all those things because we're going to use it. And for instance, we know that you had to have pre-calc, and we know that pre-calc taught you how to do graph analysis for specific polynomial functions. So we expect you to be able to do that at the drop of a hat. That's what makes physics hard, is it's a sort of often a capstone course where you have to bring all of the skills you've learned in all your math classes from kindergarten up through today. That makes it, a little harder in some sense than it needs to be, but in another sense is exactly as hard as it needs to be, because we're building people that can, figure out how the universe works, or at least help predict how the universe is going to behave. Okay, that's a big task. To do that, you really have to be mathematically and logically crisp. Your brain needs to be very good at picking up logical errors and mathematical errors and stuff like that. And does anybody have any questions on how I did these two? Okay. Now, the other thing I wanted to mention to you, and we got a little bit of time, is relative reference frames. So I use this formula over and over again, and it works in general. So let me give it to you. So re let's say relative velocity. And you can check my other uh, videos online. Just do a search for kinematics on my YouTube channel, and you'll find a bunch of pages there where towards the end of the class, I'm doing an example just like this. But let's imagine, for instance, if you had a flatbed truck, you could actually use the flatbed trailer of the truck as a number line, and you could set up your own coordinate system on it, and you could measure everything with respect to that coordinate system. And then that truck could take off and start going 60 miles per hour down the road. So how do you relate the velocity that the truck or someone in the truck is measuring from their coordinate system versus the one that you're measuring from your coordinate system that's probably tied to the ground? That's what relative velocity is. Okay. And I have a neat little equation. Watch how I write this and listen to my explanation. So I'll say the velocity, notice the reading of how I'm saying this. The velocity of object A as measured by object or reference frame C. So it's the object A's velocity measured by C's reference frame or C's coordinates, that sort of thing, is equal to, I'll put a velocity and I will put the first subscript as the exact same subscript as the first one here. That's critical. You actually have to know to do that. And I'm going to leave a space for the other one. Then I got to put a plus. Then I got to put a V again. And I got to add a space for the first one. And guess what I'm going to put for the second one? Okay. So your formula is always going to work as long as the left two subscripts match the left subscript of one of them, and the right subscript on the left-hand side matches the right subscript of the other one. Okay. That's the first part. The other part is the two missing subscripts. They just have to be the same. So what I'm going to write in here is B and B. Okay. Now, that's all well and good, and I can actually put vector symbols over top of it if I want, but in one-dimensional motion, it's not necessary to do that. But there's another thing I have to tell you, and that is the velocity of object A as seen by object B is equal to the negative of the velocity of object B as seen by object A. Okay. Now, what that means is if you're riding north down the interstate and you consider north to be your positive x direction, all other reference frames has to agree that that's the positive x direction. They don't have to agree on the origin or how fast it's moving by, but they have to agree in some sense on the directions being positive and the x-axis pointing a very specific way, the y-axis another way, and so on. So if you are traveling at 60 miles per hour due north, you would consider your velocity positive 60 miles per hour. Uh, if a car was headed towards you, maybe in the same lane, even like a head-on collision type potential, and it was moving, let's say, at 40 miles per hour, then you would say in your reference frame, that vehicle is moving towards you at 100 miles per hour. Its velocity is negative 100 miles per hour, right? That's the velocity of B as seen by A. Now, if you ask the person in B what our velocity was, they have to agree that it's positive. So we've already changed the sign, right? But they would say that you're moving towards them at 100 miles per hour. Okay. And they would say it was positive. So that's why the VAB is equal to the negative VBA. So now I'm going to quickly work this problem. Here's Mother Earth. Here's spaceship A. And it is moving. Velocity of A as seen by Earth is equal to positive 3/4 the speed of light. Now, over here is another spacecraft headed towards it, and that spacecraft is labeled B. And the velocity of B, as seen by Earth, is equal to negative 7/8 C. To make matters worse, this is a Star Trek episode all of a sudden, and this thing has shot a photon torpedo, and the velocity of this photon torpedo is V sub P relative to B is equal to negative C, the speed of light. So this C just means the speed of light. I'll just tell everybody right now, C is equal to 299,792,458.0 with a bar over it meters per second. But we're not even going to have to use that. It's also 186,000 miles per second. It's also, I think, 670 million miles per hour. So really, really fast. But if I ask you, what is the velocity of object B according to object A, if we're coming towards each other, you just add those velocities, like 60 plus 40 gave me 100. So we sort of expect that same thing to happen, but we also expect that everybody understands it's moving to the left, so it has to be negative. So what is VBA? Well, according to our solution, VBA is equal to VB plus V space A. And I look up there and I have a VBE. So I'm going to put an E here, which means I have to have an E there. So that's the formula I'm using. But I put the E in the wrong place. Hold on a second. But notice the VEA is not something that I have. Well, that's why I can use this. So now I can say that's VBE. And if I want to flip the order of these subscripts, I just change the sign. So I'm going to write it as negative VE or VAE. Okay. So now I actually have those values. The velocity of B as seen by E is negative 7/8 C minus, now the velocity of A as seen by E is positive 3/4 C. 3/4 is the same thing as 6/8. So 6/8 plus 17/8 gives me negative 13/8 C. That is how fast it would be going. And you can see that that's negative like we expected. We could also ask, what is the velocity of the photon as seen by A? And in that case, we're going to say, oops. In that case, we're going to say V photon A is equal to V photon B plus VB A, because it has to be the matching in the middle and the matching on the outsides. The velocity of P as seen by B is in fact negative C. The velocity of B as seen by A is what we just calculated. So that's plus negative 13/8 C. So you end up adding 8/8 plus 13/8. 13 plus 8 would be 21. So this is negative 21 over 8 C. And that's how relative velocities work. Now, the only part I wanted to let you know, and it's time to go now, is for extra credit, you can do all these same calculations, these same exact two calculations, but using a slightly different formula, which is the one that Einstein came up with. And if you do that, you can have extra credit points. The formula you're going to use is VAC is VAB plus VBC over 1 plus VAB, VBC over the speed of light squared. So this C in the squared down here, that's the speed of light. All the other ones are just the C's that I was using. So if you go back and repeat these calculations, you're going to see some really neat results, and you can turn them in, and that'll give you another extra credit on a homework. You folks are completely free to go. Don't forget to turn in your sheet for your syllabus. At the end of the syllabus, there is a document that you're supposed to cut and paste into a Word document, fill out, make into a PDF, and email it back to me. I'm supposed to drop you guys if I don't have that to me. So make sure you get it to me today. Today's the deadline. I'm going to check it Monday morning. If it's not there, then I have to do the dropping. So make sure y'all get that done. Do not wait. Please get it done ASAP. If you haven't already chatted me your first and last name, please do. Other than that, you guys are free to go, and I'm waiting for the last person to leave before I do, just in case anybody has any questions. Thank you. Hey, Aiden, Daniel, y'all got any questions? Oh, Aiden's gone.
I don't really have any questions regarding the material,
Uh-huh.
but when do the labs usually get graded?
Most instructors normally take, for the first lab, they usually take 2 weeks. but from there on out, it's usually roughly a week or two. Uh, in my case, I'm planning on grading all my labs tomorrow, but that's just the first lab for each of my classes.
And this schedule is really great for the lecture and the asynchronous lab. Are you going to do part two during the summer?
We hadn't thought much about that because we generally don't offer anything online during the summer. But if that's something you really want, I might be able to make that happen, whether it's online or not.
Yeah, that would be really great. I'm starting asynchronous electrical engineering next
Okay,
fall, so I'd
gotcha.
like to knock out some of these kind of like core
Prereqs.
curriculum classes first.
Yeah, I have two other people that have already asked me about the same thing. So even if we don't, you can sign up for the regular course, and I'll usually work a deal with you where as long as you know there's some danger in this and it's a lot harder to pass this way, I can make it an online class for you.
Yeah, that would be great. Yeah, I work full time and typically get home around 4.
Yeah, that kind of stinks, right?
Yeah, it's rough, but we're
With
making it work.
well, do give these two relativity ones a try. You're going to see something really cool. Like even though that's 13.8 C, you're going to get really, really close to C, but you're not going to pass C. And even weirder result with the second answer, the -21/8 C. But anything else you had? Any other questions? I'm sorry, I was excited about relativity. ADD got me.
Yeah, that was really it.
Okay,
Look forward to next class. Thank you.
cool. I hope this helped you. Have a good one, bud. Okay, so I guess that's about it. Looks like I've got all the messages done. Thanks again, everybody. Bye bye.